Welcome. We're going to get into a really pivotal review today, one published in the journal Science back in 2025. It's called Challenges and Opportunities for Quantum Information Hardware by David Oshalom and his colleagues, and it tackles some huge questions. As always, you can find links to the bibliography right there in the description below.
Right, and that's exactly what we're going to unpack. If quantum computers are supposed to be this incredible future technology, why does the hardware today feel kind of stuck? The authors of this paper make a fascinating argument that the path forward for quantum is actually hidden in the history of the digital age, and that's what we're going to explore.
Okay, so to really get where we're going, you first have to understand where we've been. Let's take a quick look back at the absolutely incredible story of classical computing.
Just look at this for a second. On the left, you've got the Intel 4004 chip from 1971. A breakthrough, for sure, with 2,300 transistors. Now look at the right, a modern GPU with 208 billion. That leap is almost impossible to wrap your head around. It's not just progress, it's a complete reinvention of what's possible. And that journey, that's the blueprint the authors say quantum needs to follow.
And a leap like that doesn't just happen. The authors argue it was driven by three key principles from Silicon Valley's playbook. First, a top-down approach where the need for better computers drove the research, not the other way around. Second, shared science. Companies that were fierce competitors still collaborated on fundamental pre-competitive research. And third, and this is a big one, patience. Just look at EUV lithography, the tech used to etch today's chips. It was a complete game changer, but it took over 20 years of hard work to get it from the lab into manufacturing. 20 years.
All right, so with those lessons from the past fresh in our minds, let's turn to the quantum world of today. It's a pretty crowded field, so who are the main contenders in the race?
This chart is basically a family photo of the leading quantum platforms, and you can see right away there's no single winner. You've got superconducting qubits, trapped ions, photonics, a whole zoo of different approaches. Each one has its own strengths and weaknesses, and they're all at different stages of maturity. It really feels a lot like the Wild West of early electronics, before silicon came along and dominated everything.
And this quote from the paper is absolutely crucial to understand. Just because a technology has a high technology readiness level, or TRL, doesn't mean it's anywhere near finished. It doesn't mean the science is solved and it's just an engineering problem now. All it means is that we've reached the starting line. These systems, even the most advanced ones, are really just the beginning of the journey toward powerful, fault-tolerant quantum computers.
But here is the massive problem. With classical computers, we could just keep shrinking transistors. But in the quantum world, simply trying to add more qubits, the quantum version of a transistor, is just not working. The entire field is slamming into a gigantic scaling wall. And that wall is basically built from four huge, fundamental hurdles that every single platform is facing. First, materials and fabrication. Making quantum-grade materials at scale without any defects is unbelievably hard. Then you've got what's called the tyranny of wires. Managing the millions of connections needed to control the qubits is a nightmare. These things also need insane amounts of power and cooling. And finally, you have to perfectly calibrate and control every single component. It's just a monumental challenge.
Okay, so if building a single giant monolithic quantum chip is basically a non-starter, what's the way out? Well, the paper proposes a really elegant, radical shift in thinking. Let's stop trying to build one big perfect thing. Instead, let's build lots of smaller, good enough things and then link them together.
And this is the central idea, modularity. Honestly, the best way to think about it is with Legos. Instead of trying to carve a giant complex spaceship out of a single massive block of plastic, you just build it from smaller, simpler, specialized bricks that you can connect together. It's a much smarter way to build something complex.
So, it all starts here, with a single, self-contained module. This little building block might be specialized for processing or maybe for quantum memory. And because it's a self-contained unit, all those huge challenges, the wiring, the power, the cooling, the calibration, they're all capped at a much more manageable size. Then, here's where the magic really happens. You start connecting these modules using specialized, high-fidelity quantum interconnects. This is how you scale up. You just add more modules, creating a much more powerful system, all while completely sidestepping the problems you'd get with one giant monolithic chip. And this is what the future might actually look like, a full rack-based system. It actually looks surprisingly similar to the classical data centers that power our world today. So the future isn't one giant quantum brain. It's probably going to be racks and racks of these powerful, interconnected quantum Legos, all working in concert. So this whole modular vision, it's not just a cool idea. It gives us a practical, real-world roadmap for actually building these things. It tells us what to focus on and what to watch for in the coming years. So for all you science professionals watching this, here are three key actionable takeaways. First, view this whole thing on a historical timescale. Remember the 50-year journey of the classical computer? This is a marathon, not a sprint. Second, and this is critical, watch the interconnects, not just the qubits. The big breakthroughs won't be just about qubit counts, they'll be in the technology that links these modules together. And third, expect a hybrid, heterogeneous future. It's probably not going to be one size fits all, but a mix of different quantum technologies working together.
And this really brings us to the core message. If you remember one thing from this explainer, make it this phrase: from monoliths to modules. The next great computing revolution isn't going to come from building a single bigger mountain. It's going to come from building brilliant bridges between many smaller, more powerful islands.
All right, so to wrap it all up,
we've seen how the incredible lessons from our own digital past are giving us a map for the quantum age. The key to breaking through that massive scaling wall and building a truly flexible, powerful quantum future seems to be this shift from monolithic designs to an interconnected, modular architecture.
So here's your call to action. As you follow the progress in this field over the next 5 years, pay very close attention to advances in the interconnects, especially photonic interconnects. That's using light to link these modules together. That's the engine. That's the technology that's really going to drive us from this transistor age of quantum computing into a true quantum era.
Thank you so much for joining us for this explainer. The disclaimer and a link to the full bibliography are in the description.